So last time we looked at given a parameterized curve, or let's just say given a curve C in 3-space with parameterization gamma of t for t, say between A and B, its velocity, right? We introduced velocity is the vector gamma dot of t, all right? So this is the same thing as, say, dx dt, dy dt, dz dt. Acceleration is the vector, right? So acceleration is a vector with second derivatives in each of its components. And the speed is the magnitude of the velocity at each point. And if gamma t traverses C exactly once, we also have the fact that then the arc length of C is given by the integral from A to B of gamma dot t dt, right? You're integrating the speed across your parameterization, assuming that you traverse your curve exactly once. All right, so those were the key properties we saw last class on parameterized curves. And we also saw that with these fundamental quantities, right, first of all, there's a very physical meaning to these, right? Velocity gives you the direction and also the speed at which you're moving. Acceleration is how fast your velocity is changing. And what we also saw was there's also the unit tangent vector at each point. So if gamma of t is equal to p on this curve, so at some time on this parameterized curve, you're at some point p, then there is a unit tangent vector at that point. And that's given to you by the unit vector of the velocity divided by the speed, all right? So this is the vector that is pointing in the direction of your movement according to your parameterization, but it has unit length, right? Because you're dividing out by the magnitude of the velocity, the speed. And so this is because, if you have a curve, visually speaking, you can move along this curve this way or backwards, right? Really, the direction at which you travel, it could only be of one of two directions, right? It could be this direction or that direction. So the unit tangent vector is really, it's unique up to a sign, all right? So, and it's independent of your parameterization. Really, what it's only dependent on is the direction at which you travel. It doesn't matter how fast you're traveling on this curve. You could slow down here, you could go really fast here. The unit tangent vector, when you calculate it using like this, using this formula here, it's always going to get you, the direction of travel. So there's one or two directions it could be, but up to the direction difference or up to a sign, it's uniquely determined. And now that you have a velocity, or even a tangent vector if you want, you could have the tangent line to the curve, all right? So the tangent line to C at P is given by, or it can be parameterized by the following. It could be just the coordinates of P plus T times your velocity vector. Or it could also be P plus T times your unit tangent vector at the point. All right, maybe there's too many T's going about here, so I should put, because T is a parameter of gamma that brings to this point here. Maybe I'll parameterize the line by L of S. The dot notation. Sorry, yes, the dot notation here means this. So I should say alternative notations. Gamma of t is sometimes identified with a position vector. Gamma dot of t is sometimes called r dot of t. Gamma double prime of t is sometimes called r double prime of t, amongst various other notations. Right, so what did this buy us? Well, the tangent line tells you the trajectory of a particle that is undergoing it's undergoing inertial movement, or it's experiencing no force, right? So once again, the analogy was, or the example last time was, if you're a particle and you're actually a spaceship and you're traveling along this path in space, and all of a sudden your engine's cut out at this time where you're at point P, then at that precise point, if you're experiencing no more force, then you'll be flying along a straight line given by this line in green here. Okay, so that is that's the physical meaning of the tangent line to the point. The geometric meaning of the tangent line to the point, I mean, it's a straight line that that approximates to first order your curve at this point. All right, it's like the best straight line approximation to your curve at P. That's perhaps a mathematical definition or intuition of what the tangent line is. And what this also buys you is you can now interpret the angle between curves. All right, so we were working on an example last time, which we should finish, which is if you have two parameterized curves, you can ask the question of whether these curves cross at a point P. And whether they do or not, well, if they do, you could further ask what angle these curves make. And when you're asking the question, what angle do these curves make when they collide or when they intersect? What you're asking for is what is the angle between the tangent vectors of the curves at those points. All right, so it makes sense now to ask for the angle of intersection between curves. Previously, right, we've been able to say what it meant for the intersections of lines with planes and other straight, linear or straight line objects with planes. Now you can make sense of intersections of curves that are not straight, things that are curvy and all that, as long as they intersect say a plane or a line, that you can make sense of the angle of intersection just by taking the linearization or finding what the tangent vector is at the point and then doing the angle calculation with a vector at that point. So let's revisit last time's lecture. At the end, we had this curve here, which I'll copy. Right, so we had two curves here from last time. One of them is a line, the other one is not a line. We asked if these curves intersected, and whether you figure out whether curves intersect or not, what it depends on is you have to solve a system of equations here. Because you're not necessarily asking yet if these trajectories of particles, if they are trajectories of particles, whether they're colliding at a point or not, you really just want to see if their paths intersect. You're allowed to set one of the parameters here. You're allowed to set the second parameter different than the first parameter. So what we got was, we solved this. We looked for solutions to the system for T1 to satisfy T1 and T2 for these respective parameters to satisfy the system of three equations. Once again, this is if you count the variables here, you have two unknowns, T1 and T2, and you have three equations. All right, you have more equations than unknowns. That's something called an overdetermined system. So it's quite possible for this to have no solution at all, in which case it doesn't collide, or sorry, in which case it doesn't intersect. In our case, we sort of went one by one and saw if there were a solution, what the solution had to satisfy. And fortunately, we were able to deduce an actual solution to this, which meant that there did exist an intersection point at these two respective parameters. All right, at T1 is equal to -2 and T2 equals to 3. We had a second part of this, which was if these actually modeled the trajectory of a particle. All right, so they share the same parameter T. You start them at the same clock, right? Do these particles actually collide? And we realized that because we had the answer to the first section, we knew exactly where the intersection points are. In this case, there is a single intersection of 4, 6, 5. So really, if particles collide, they would have to collide at the intersection points, at one of the intersection points. But because of our calculations here, we found that, well, T1 is at -2, which is definitely not equal to T2 at 3. So these particles do not collide. All right. In other words, for a particle to collide, you would have to solve this system here for the same variable. You're not allowed to do T1 and T2 here. You have to solve them identically for T. Okay. So really what we wanted to do next was find the cosine of the angle of intersection, right? So they intersect at this point at 4, 6, 5. For angles, right? For angle of intersection, we need the velocity or unit tangent vectors. So in this case, we look at gamma 1 dot of T. And so gamma 1 is given to you by this parameterization. So what's the velocity of this? So in chat, does someone want to give me the velocity vector of gamma 1 of T? So right, so in this case, this is 2T, and this is -1, and there's 0 here, right? So, and for gamma 2, dot, well, this is just a line, just look at the direction vector, or you could also differentiate. The direction vector is coefficients of t, so when you do ddt of these, this is 0, this is 1, and this is minus 1. All right, so what is the angle of intersection? Well, we need these vectors at a particular time. So at the point 465, what are the relevant velocity vectors at 465? So remember, at your curve, your first curve arrives at 465 at t1 equals minus 2. Your second curve arrives at 465 at t2 equals 3. So what are the velocities? What's the first velocity? And what's the second velocity? Right, so for gamma 1 dot, I need to plug in t is equal to minus 2. So that's minus 4 minus 1, 0. And gamma 2 dot is, I need to plug in t2 is equal to 3. But there's nothing to plug in, so it's still 0, 1, and minus 1. Now, what do we have? We have the fact that if the angle, let's say if this is gamma 1 and gamma 2, and this is the angle, and we want the cosine of the angle between them, then we know that cosine theta is equal to what? Well, it's equal to gamma 1 dot over the magnitude of gamma 1 dot dotted with gamma 2 dot over its speed, right? It's the same thing as t1 dotted with t2. So what is this? Well, we could check. You calculate gamma 1. Let's if you don't want to do the unit tangents, then let's do the dot products first, right? So gamma 1 dot gamma 2 is minus 4 times 0, which is 0, plus minus 1 times 1, which is minus 1, plus 0. So that's minus 1. And now the speed of this first curve is going to be 16 plus 1. So that's 17. And you got to square root that. So that's root 17. Gamma 2 dot is 1 squared plus 1 squared. That's root 2. What you end up with is you get the cosine of theta is equal to minus 1 over the square root of 34. So here's a question, a separate example now, perhaps a more conceptual one. Suppose your speed is constant, all right? Suppose gamma dot of t is constant. What can you conclude about the acceleration? So in one variable, we know that if your speed is constant, then you have a constant. Your speed in that case is just, you don't even need to put bars around it, right? You just have a constant, and you differentiate a constant to get acceleration, but you differentiate a constant at 0, so you have 0 acceleration. But now let's look at this scenario in our setup here. So first, to make things easier, okay, so we have the fact that the speed is constant. This implies that the speed squared is also constant. All right, that's hopefully not a two. What I did here seems pretty useless for now, but if you square a constant, it's still going to be constant. But what this buys us is the dot product of this is constant with itself, right? Because remember, if this is a vector, the norm squared of a vector is just the vector dotted with itself, right? So what is this dot product? Well, this is the same thing as its components, x dot t squared plus y dot t squared plus z dot t squared is equal to constant. And so what I could do is, well, these both sides are equal, so I could take time derivatives of both sides. Now, what's ddt of the constant on the right-hand side? Well, it has to be 0, right? Because if this is like a constant 5, then, differentiate a constant, that's 0. Now, let's do, on this left-hand side here, does someone want to give me a term for, let's say, ddt of x dot squared? So remember, x dot is dx dt. I have dx dt squared. I'm taking a time derivative of this. So what expression should that give me? Just for this x term. So there's x dot t, but remember there's a squared here already in this first term. So I can't just immediately do x dot t. There's certainly x dot t, but what do? I got to do chain rule. So what does the chain rule get me? This gets me 2x dot plus 2y dot plus 2z dot is equal to 0. Now, is there a nice way of writing this here? Maybe in a vector formula, right? So we have a vector x dot y dot z dot. That's my velocity vector. And I just gave it away. But x dot y dot z dot is my acceleration vector. So what does this tell me? This tells me that 2 times the velocity vector dotted with the acceleration vector is equal to 0. Now, what does this tell me about the acceleration? Can it be non-zero? And this could still hold true. Well, okay, so let's assume speed is not 0. Speed is not 0. Let's say this velocity is not 0. Is it possible the acceleration to be non-zero and this still hold true? So this is the dot product of one vector and the dot with another vector. So is it possible for the dot product of two different vectors, two non-zero vectors, to be 0? And the answer here is yes, as long as they're 90 degrees with each other. All right. So what you find here is, therefore, your acceleration is perpendicular to your velocity vector at each point. All right. So this is one situation here which drastically deviates from the one variable situation. All right. There are many ways when you take derivatives of vectors. All right. Things change, and just because the magnitude of your vector is constant does not mean that the derivative of the vector itself has to be 0. Here, the magnitude of your vector is constant, but the derivative of the vector itself is merely perpendicular to your original vector. And now this formula, okay, so I have a question. Is this formula true only when the velocity is constant? Well, you have to specify which formula here. All we've done here were calculations. The calculation on the left-hand side is extremely valid, right? One thing you could know from this calculation is what we just showed was on the left-hand side, d dt of this is the same thing as d dt of this dot product, all right? You have two vectors here. They happen to be the same one. And you're taking the time derivative of this dot product. And what we've seen here on the left-hand side is basically the product rule applies with the dot product, all right? The dot product of this, if you differentiate it, is the same thing as you differentiate the first one, and you dot it with this. So you get gamma dot 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 gamma dot, and then you add to that the derivative of the second one dotted with this, which is gamma dot with dot product gamma dot dot, and those are the same. So you add them together and you get 2 gamma dot product gamma dot dot. So this left-hand side always holds true. It's the right-hand side that differs, right? If your velocity is not constant, you cannot conclude that your derivative of a constant is 0, right? Because it's not necessarily constant, so you wouldn't have this. But certainly, if you have speed that's constant, then your acceleration has to obey this. So questions here: physically, if an object is moving at constant speed, wouldn't acceleration still be 0? No, that is not true. So the classic example here, right, is if you imagine yourself, the point here is, let's do this, all right? Do the next example. Let gamma t be the following. Let gamma t be cos omega t sine omega t, where omega is constant. Find the acceleration of gamma. Okay, so first of all, in chat, what is this curve here? So what is gamma here parameterizing? Right, it's a circle. Now, if you've seen, remember your physics, you know what omega represents, the frequency, but we could also calculate this. Gamma prime, the velocity, is minus omega sine omega t. And then we have omega cos omega t. Now, for good measure, we also know that its speed here, right, is constant as speed omega, right? If you want to do the speed, you do this squared plus this squared and square root it. Well, sine squared plus cos squared equal 1. You factor out omega squared square root, and that's absolute value omega. And this is constant speed. Its acceleration, we could calculate directly here as well. Take another derivative, and you get omega minus omega squared cosine omega t, and then you have minus omega squared sine omega t. And observe gamma dot dotted with its acceleration. Well, what is this? This is, if you want to take these two vectors and dot them together, look at this and that, then this is equal to omega cubed sine omega t cos omega t minus omega cubed sine omega t cos omega t, which is equal to 0 as predicted. So in this case, you have the curve gamma t here. You have some velocity vector, gamma dot at t, So at each point here, really the velocity vector is constant speed, which means the length of the velocity vector is the same. The length of these red arrows are always the same, but clearly they're not the same vector, right? Because this vector here, you can't just drag and drop here and have the same vector. This turned. It went from this to this. So remember that in our calculation of derivatives, when we take the derivative of the vector gamma prime, what we're doing is we're taking ddt of the components, right? But really what you're doing is you're comparing this, the change from this vector to this vector as these points get closer and closer together. All right, so this vector turns a little bit to become this vector, and you want to compare the difference vector of that with the change in time, right? And when you take that limit, that's what exactly this derivative is actually getting you. So it shouldn't be surprising then that even though the length of these vectors are constant, because the direction is changing always, the acceleration, or in other words, how fast gamma prime is changing as a vector, is not going to be zero. All right. In this case, we actually have something like this. So in this case, this is gamma dot dot of t, and it always makes right angles with your velocity vector. Any questions here? Right. So if you recall, your physics, this is where the centripetal force comes from. When you swing, say, a ball on a piece of string, maybe across your head or something, or if you're an athlete and you're trying to throw a discus, right? You're spinning around. There is some force. There's tension in the string that is always keeping the ball in orbit, or in the proper circle, or before you let go of the discus, there's tension in your arm to keep it where it's supposed to be without flying off. And that tension there is applying a force, right? Tension you can think of as a force. Force is, according to Newton, right? It's up to a constant, the same as acceleration. So here, there's always going to be a force drawing you inwards when you're traveling at constant speed around in the circle. All right, right. So maybe I'll just mention this. So we skipped a lot on curvature and torsion and things like that in chapter 13. That stuff's not going to be tested, but just for completeness sake, because you can't really go through all these parameterizations without mentioning it. I will mention that this material is not going to be tested, but let me just mention that there is this quantity called curvature. All right, so curvature is, so this is not tested. The curvature is a measure of how the unit tangent changes. In a sense, from what we've seen over here, the given a parameterization gamma of your circle here, and in our case, we've chosen a parameterization that's nice. Okay, so we've chosen constant parameterization with speed omega, and in this case, when it's nice and constant, when your velocity vector has constant length, the acceleration vector is always pointing at right angles to it, and in a sense, it measures how your path is curved, right? But in a sense, right, if I just drew a circle for you of this exact same radius, I didn't give you any parameterization, it would be nice to have a quantity that quantifies how curved this circle is, right? The issue here is, depending on, we can't just take acceleration, because if I parameterize this, say with omega equals 100, then your acceleration has like magnitude 100, has like a magnitude 100 squared, right? Basically, your acceleration itself depends on how you parameterize the curve. But there are quantities, right? Just like arc length is a quantity of a curve, that we don't want to depend on how you describe or parameterize a curve. We want a measure of curvature that does not depend on how you decide to parameterize your curve either. So curvature is the sort of measure. So curvature is a measure of how the unit tangent changes. And roughly speaking, so it's given a parameterization, curvature K is the following. K is given to you by the absolute value of how the tangent changes over your speed. All right. So what this is, assuming that you have an expression for your unit tangent vector in your parameterization. Remember that up to a sign, we've gotten absolute value bars here now, so it doesn't even matter your sign now. Your tangent vector, your unit tangent vector is unique to your curve. All right. It does not depend whatsoever on how you describe your curve or how you parameterize your curve. Your unit tangent is your unit tangent. It's intrinsic to this curve itself. And to calculate this curvature quantity, you want a measure of how it changes. So depending on how you parameterize it, there's a parameter t. So you want to describe how your unit tangent changes with the parameter t. That's this derivative here. And then you divide out by the speed, right? Because the speed is sort of one thing that is not intrinsic to the curve. Your speed depends on how you describe the curve, how you parameterize the curve. So you sort of just normalize this whole thing in a sense by dividing up by the speed again. But this is roughly speaking what curvature is. In your textbook, you'll see a lot of random, a lot of different ways of expressing curvature as they come up. But fundamentally, this is what this quantity is. Right. So that's basically it. I don't think I have anything more to say about this. As a fun exercise, maybe you could calculate the curvature of a circle of unit 1 here, of unit radius here, if you really want to. But I'll leave that as an exercise. We're not going to test this in this class, but it's good for you to know. So that concludes curvature. That also concludes what we're going to talk about for now on parameterized curves. All right. So this material is going to be tested immediately, next week, but also, much later when we go into vector integrals of vector fields over curves and all that, they'll make a comeback, all right? So make sure that you really do understand how parameterizations work, their associated quantities like velocity and acceleration, and, basically what we covered, minus curvature. So let's move on to something quite different, which is now chapter 14. And these have to do with functions, now multivariable functions, in the sense that these are functions that take as input, say, variables that you could think of in R2 or R3 or even more, and they spit out a single number. All right, so these are multivariable functions. And thus far, we've seen functions of one variable, so our parameterizations, that take in one variable and output 2 or 3 variables. All right. So in a sense, what we say is the domain of our parameterization is one-dimensional, and the output or the range of our parameterization is 2 or 3-dimensional. So in other words, the domain of gamma was one-dimensional. The range of gamma was higher dimensional. And now we're going to flip this on its head, and we're going to take a look at functions. We're going to analyze. We're going to do derivatives of these functions that are that take in several variables and only have a range of one variable. So now focus on f with domain in R2 or R3 or higher and range in R. All right, so they take in several variables and they spit out one. We've seen examples of this earlier as sort of if you express surfaces, right? Certain surfaces are expressed as algebraic equations or functions that take on a certain form. For example, x squared plus y squared equals 1 in R3, while your function is x squared plus y squared, and when it's equal to 1, it represents this sort of surface. All right. In this case, let's start off with an example, which is the following. On the domain and range of the function f of x, y, z is equal to natural log of z minus root x squared plus y squared. So when I don't explicitly express a domain, it's common practice to assume that your function given is on the maximal domain it could be defined. All right, so there's regions where this function cannot be defined, and that's not part of the domain, but this function can be defined on a certain domain. So in this case, how many variables are there in this function? This is a function of how many variables, right? So its domain is somewhere in R3, but we could do better than that. What do we know about natural log? What can you feed into natural log? What must this quantity satisfy? Right, so natural log must take in strictly positive quantities. So we need the domain. We need this quantity here to be strictly greater than 0. All right, so in other words, we also need z to be strictly greater than x squared plus y squared. And how might we accomplish this? Well, we could also do z squared. If z is greater than the square root of x squared plus y squared, then we must have z squared is greater than x squared plus y squared. Now, what is the surface z is equal to x squared plus y squared? So it's not a circle, no. Right? If it were a constant, x squared plus y squared equals constant, that's a circle. But what's a surface now? This is now in R3. So what z squared is equal to x squared plus y squared? So this was one of the surfaces that we've taken a look at. So a paraboloid would be z is equal to x squared plus y squared, but we want z squared is equal to x squared plus y squared, right? So generally an elliptic cone, but in this case, what's the ellipse? Well, in this case, this is a cone. this is a circular cone. So what we have is the following domain. So this is a domain z squared. This is equal to x squared plus y squared. And what we want is the inside part of this. All right. Actually, sorry, I should have drawn only one part of this. This was this surface here. It's nice to see as a double cone here, but you really want this part to be positive. So, you know, if this bottom cone were included, you would have parts of z which were negative, and let's say at 0, 0, negative 100. If I were to fill in this cone here, that would be a point here, but you know, minus 100 would not work for a natural log. So in fact, you could only have the top part of this. So this is a domain. The range of this, what is the range? So the range is the values that f is allowed to take. So if f is the natural log of z minus x squared plus y squared, natural log of anything, what might the range be? Right, so it's minus infinity to infinity, because that's the range of natural log. And furthermore, this region here is the usual domain of natural log, right? It goes from your values and your inputs range anywhere so long as this is positive. So this is positive. This is from 0 to infinity. So natural log from anywhere from 0 to infinity does span the entire range minus infinity to infinity. So here, this is the range. I mean, the range is, so we have a question about images. I think images are, I mean, in the one-dimensional case, it's the same thing. Your range and image of your function, they're the same. It's the same terminology, all right, for image and range. It's when you have functions that take in, let's say, a function of two variables that map also into two variables, for example, where usually those are called, you know, the range of those are usually called images, and we'll figure out a way of how to sketch out those when we come to it. All right, so right now we're only focusing on functions that take in several variables, but they always output only in one variable for this section so far. Okay, so how can we picture functions f of xy, or let's say f of xyz? Because, well, we just drew a bunch of examples for parameterizations, right? We could picture, in certain cases, functions of one variable in time and how they map into 3 dimensions, say. We would like to do sort of a similar thing for functions of multiple variables. Now, there's an issue here because, especially in this case, all right, so if we just focus on the two variable case, f of xy, we're still able in certain cases to sort of graph out what this looks like, right? So in two variables, this is a major question here. This is f is a function of two variables. We can look at the graph z is equal to f of xy, right? That just means for every input, x and y, I just look at what number this function spits out and I put it on a graph, right? So for example, we've seen some of these already, right? For example, if f of xy were equal to x squared plus y squared, then what would the graph of this look like? The graph of this would be z is equal to x squared plus y squared, and what is that? Not a circle, not a cylinder either. The cross sections where you're looking at x squared plus y squared equals constant, those are certainly circles, right? And we'll get to that. But this is going to be a paraboloid. The paraboloid looks like this. So in this particular case, right, for a very restrictive set of examples for say, surfaces we've seen already, we know what the graph looks like. Now, how could we deduce this in general? Well, we could also take what are called contours, which we've already seen in disguised form, all right? So look at contours. F of xy is equal to k, all right? So these correspond to the z equals k cross sections of some surfaces we've seen previously. All right, so what I mean is you can look at the contours of f of xy is equal to k, which means in this case, we still have our function x squared plus y squared. Its contours are of the form x squared plus y squared is equal to k. And we could plot this out. Its contour at k equals 0 is 0. K equals 1. It's a bit off center, sorry. This k equals 1. And then k equals 2 actually goes up to root 2 here. K equals 3 is a circle of radius root 3. Or sorry, k equals 3 is a radius root 3 circle. And what you could see here is what we're seeing is, once again, you're slicing this at constant z, although in this particular case, it might be useful to imagine that you have this picture down here. So you have these contours all down here, and the kth contour, the contour at f is equal to k, gets raised up to here at z is equal to k. And so you're sort of, you have all these rings sitting in 2 dimensions, and how high these rings go, is dictated by height k. So at height k, your ring is going to look like your contour f of xy is equal to k down here. And whatever that one-dimensional shape looks like, you imagine lifting that wire up or down along z, and you could build your shape from there. All right. So this seems like a much more involved process, but in essence, what this is doing is, you have contour plots, which are essentially the z equals k cross sections of the surface z is equal to f of xy, and then you could imagine what your graph looks like then, and that's how you could imagine your function. Okay, so this is another name for the traces, although in general this is a bit more general, because what you'll see is this is for 2 variables. Now, if you have 3 variables now, you're kind of doomed, right? Because we can no longer graph a function of 3 variables now. We're out of room now, right? In 1 variable, it was nice, y is equal to f of x. We could picture that. In 2 variables, f of xy, we could picture z is equal to f of xy. Now, if you have 3 variables, f of x, y, z, and that's your function of 3 variables, and you want to picture your function of 3 variables, then you're out of luck, because you cannot graph it any longer. All you could do, the best you could hope for, is look at the contours. Now, the contours go by another name when there's 3 variables. They're called the level sets sometimes, but that's really the only choice you have. All right, so for functions of 3 variables, so f is a function of x, y, and z, you cannot graph it anymore. You've run out of dimensions. So all you really have is the second way here, to look at the contours. So in your mind's eye, you have to realize that now your contours are of the form f of x, y, z is equal to k. And as k ranges, you're going to get a family of surfaces now in 3 dimensions. And these are sort of the 3-dimensional shadows, or sorry, the surface are 2 dimensions, right? So these are 2-dimensional shadows ranging in 3-dimensional space. And you can't actually see the graph. You can only see where the parts where your function are constant. So here you need to adapt the contour method. So the contour method is you look at level surfaces of the form f of x, y, z is equal to k. All right, so here's an example. What are the level surfaces of, say, f of x, y, z is equal to x squared plus y squared minus z? All right, so this is like trying to graph something in R4, but you really don't have R4, right? You could always graph this in R4, but that doesn't really help us because none of us could really draw that. So in this case, what are the level surfaces of this? Well, you could write x squared plus y squared minus z is equal to k. And what surfaces are these? Maybe you could try z is equal to x squared plus y squared minus k. So this is not a cone, right? A cone would require z to have z squared here. It's also not a hyperboloid. So let's pretend, you want to take you got to take the cross sections, but let's say k is equal to 0, right? Z is equal to x squared plus y squared. That's a paraboloid like we had above, right? Z is equal to x squared plus y squared. It looks like this. So here's what these are paraboloids, and what we have is the following. The level set graph looks like the following. Well, I shouldn't say graph. This is not a graph of your function, right? These are the level sets, or the contours of this of this function of 3 variables. And what we have is we have the contour at, or the level surface at, say, this is f x, y, z is equal to k, right? In this case, if k is equal to 0, this is z is equal to x squared plus y squared. Looks like this. Now, if k is equal to 1, does this move up or down? Z is equal to x squared plus y squared minus 1. Is that above or below this? Right. So, right, at k is equal to at minus 1, this corresponds to the level set f of x, y, z is equal to 1, plus 1. All right. In this case, k is plus 1. This moves down to minus 1 just because of the peculiarity of this function here. All right, and similarly, you could argue that as as k goes to up to, let's say, 3, this is z. This is f of x y z is equal to minus 3. All right, and so forth. So you could see that in this particular case, each of the level surfaces or the level sets. Maybe I should clarify level surfaces. These are also sometimes called level sets of this particular function. They all look like paraboloids, and that means that when you're a point stuck on any, let's say you're a point stuck on this green paraboloid, f of x, y, z on any point on this green paraboloid is going to give you 0. F of x, y, z anywhere on this red paraboloid is going to give you 1. F of x, y, z anywhere on this turquoise paraboloid is going to give you minus 3. All right, so by having a sense of what the level surfaces look like and how the level surfaces change when k changes, that helps you piece together what your function looks like. All right, so by knowing the shape of the level set, f of x, y, z equals k at each k, and how f of x, y, z equals k changes, as k changes, we can piece together f of x, y, z. I should specify, no, f of x, y, z is definitely not a paraboloid, right? F of x, y, the level sets of f of x, y, z, what were paraboloids, but f of x, y, z it's not a surface even, right? Because you can't graph f of x, y, z. You could graph it in R4, but we definitely don't have terminology for things in R4. F of x, y, z is just an arbitrary function, right? I could tell you that f of x, y, z is the production function of a factory. Let me go back here. Right, f of x, y, z here, it's not geometric at all, right? We're only trying to add geometric intuition because that's what we're comfortable with. We need to have some sort of shape to this to, to comfort us, because we used to have graphs that were very nice, but it's like, if you have a function y is equal to f of x, y is equal to, let's say f of x is equal to x squared, right? So y is equal to x squared is a graph of it. But in reality, let's say, f of x was just measuring your displacement at time x, right? So y is equal to x squared is indeed a parabola, but the function f of x squared, f of x equals x squared, which is what matters, is actually the displacement of some object. Or it could be like the let's say if for x units that you're selling for your company, you get x squared dollars in, that's just a function telling you, if you sell X many units, you're going to get X squared dollars out. The graph of it is nice and geometric, and it happens to be a curve, y is equal to X squared. That's a parabola. But in and of itself, it has no relation to, what your function is actually doing. Your function is just a function, right? It's telling you a relation between some objects. In the same analogous case here, I could give you the function, right, which I just gave you, x squared plus y squared minus z. I could say, okay, well, this is somehow the production, or let's say it's some model for how much my factory is making, let's say. Okay, so let's say x is some object A, y is some object B, and z is like the manpower to make this stuff, okay? So like the revenue I have to pay my workers. Then, for example, this could be a profit function, a very crude one, where x units sold a product A and Y units sold a product B get me this revenue, but then I have to subtract off the cost. So this is just some function telling me how much I'm making in a very crude way, right? And what we're doing here is I'm pointing out you cannot graph this function because you're out of variables to graph it. But if you want to have some sort of semblance of comfort and to actually have an idea of what this function's doing, completely theoretically, it's useful to have the knowledge of its level sets. You know that on green here, if for any amount A I sell in X and amount B I sell in Y and labor output, labor cost Z, as long as X, Y, and Z, this combination of inputs lie on this green paraboloid here, my profit's going to stay the same. All right, well, in this case, the profit's going to be 0, which is not very good, but it stays the same. Similarly, if I'm here, if I'm stuck at X, Y, Z on this turquoise surface here, then X, Y, Z could be different, but as long as it is so long as the combination of them lie on x squared plus y squared minus z is equal to -3 here, then in this case, I could still manage, right? I could still imagine what my output is. It's all the same. It's at -3 in this case. So all we know here are the contours or level sets, right? Contours, what you have to remember maybe from the textbook is they like a lot of terminology, right? So in essence, right, what we've done here was for functions of two variables, their contours are essentially the z slices, right? The z equals k slices or cross sections of the graph z is equal to f of xy. In this case, the graph of this is quite literally a paraboloid, right? If you graph the function of two variables and you look at the graph z is equal to f of xy, it's a paraboloid. The contours, right, in this case is very concretely tied to the graph of this. These are the contours are precisely the z slices of your graph when you graph it like this. When you go to three variables, you can no longer have a graph. It makes no sense to talk about a graph because you can have a graph, but it's now in R4, and that just screws us up even more, right? We cannot imagine 4 dimensions for the life of us. It's very hard. So you could only deduce things indirectly just by looking at their contours, except now you replace the word contours by level surfaces or level sets. And these are the combination of inputs that are equal to k. These are x, y, and z, such that x, y, and z, when fed into your function, equal k. In this particular case, and in a lot of cases you'll see in WebAssign, homework, and this class, these are going to be reasonable surfaces that you could, probably take a look at. So you could, if it's a matching question, it has to be one whose level surfaces you need to know some behavior of, right? So in this case, there's a lot of paraboloids, a lot of cones, and things like that. In this case, it's just purely paraboloids, and they translate up and down depending on what your k is. All right, and this is how you indirectly detect what your function is, but your function itself does not define a surface. All right, in fact, if you really want to be pedantic about it, if you have this as a function in 4 variables, it defines a hypersurface in 4 dimensions, but that once again does not help us. We just want to sort of picture what this abstract function is, and this is a good way of doing so. All right, so good questions. I hope that clarifies you. So the point here is, you can't really use graphs anymore, but we can indirectly detect these things.